Now, if you go back to the Darcy equation, how do you check that your delta P is not more than 0.5 kilopascal per meter? Now, for the straight pipe, you just let L equal to 1 meter. L equal to 1 meter, and the D is the pipe inner diameter. So your unit will be Pascal per meter. Let L equal to 1 meter. Then you can check L 1 meter, D is the pipe inner diameter. Is the pressure drop more than 0.5 kilopascal per meter? If no, means good. Your pressure loss is not too high. Do you have any questions? You just need to memorize this: 1 meter per second to 3 meter per second, and a 0.5 kilopascal per meter. Make use of the Darcy equation. Let L equal to 1 meter. Yes, indeed. You have to take the length of the pipe to be 1 meter. Now next, this one I've explained in the class. This is very important because you may be asked this type of questions. Capital costs and operating costs. Now, if you have a larger pipe diameter, capital costs will increase. Why, when the diameter of the pipe becomes bigger, capital costs increase? Because the pipe wall is thicker. The thickness has increased. If you consider 1 meter of pipe, the pipe is thicker. Your pipe is thicker means must use more carbon steel. More carbon steel means more expensive. Therefore, larger pipe diameter, higher capital cost. Now, what happens when you increase the pipe diameter? When you increase the pipe diameter, in general, the pipe diameter increase, velocity decrease. You've seen that in your CA for the heat exchanger. So pipe diameter increase. If your volumetric flow rate or mass flow rate remains constant, but you increase pipe diameter, velocity decrease. So velocity decrease will decrease the operating cost because the pump will not have to consume so much electricity. If the pump doesn't have to consume so much electricity because V is lower, V has gone down, then your operating cost will be lower. So you need to consider capital cost plus operating cost. Then that will give you the total cost. The total cost, there's a curve starting from this point. This is 0, 0. This is a non-zero. This is positive. Starting from here, you can just imagine you draw a curve. Then you find the minimum cost. And the minimum cost is not at the point of intersection. You must be given enough information before you can draw this kind of curve. But it's not at the point of intersection. Now this one, the optimum diameter, don't need to memorize this equation. The optimum pipe diameter, this pipe diameter refers to the pipe inner diameter. It's for turbulent flow. Remember, turbulent flow, usually define turbulent flow as Reynolds number more than 4,000. You've done this calculation, wall thickness, using this ASME B31 code. Can refer to your notes and exercises. Now, the thing is that you need to give allowance for corrosion. Corrosion is chemical attack. If the chemical attack the material, this material becomes thinner and thinner. So you need to give allowance. Sometimes in our calculation, the design thickness is very, very small. Obviously, you cannot have You cannot have a wall thickness that is too small. Otherwise, when you have a corrosion, very soon the chemical would eat away the material, and then the chemical will leak out. Therefore, you must include corrosion. So that's the reason for corrosion allowance. This is another method to find the schedule number. Now remember this, most of the time we use schedule number 40 most of the time, right? So we should stick to 40. Now this one shows the procedure of a pipeline sizing. Determine optimal diameter. Where you get this optimal diameter? From this here. This is for turbulent flow, carbon steel pipe and stainless steel pipe. It's the first step. Then after that, determine wall thickness. Use the formula. You've got to refer to the exercise in your notes and find the nominal pipe size and schedule that has the closest match to the inside diameter and the wall thickness calculated in step 1 and 2. These three, the step 3 here, you have to refer to a table for the NPS, the nominal pipe size. All right, you can type your questions. All right, what if they provide a length for the pipe? Now, when you check for the pressure drop, we need to make sure that the pressure drop is not greater than 0.5 kPa per meter. So over here is in terms of per meter, not the actual length of the pipe. So you still let L equal to 1 meter. The L over D, the L inside your Darcy equation. Because you're not checking the pressure loss for the whole pipe, for the entire pipe. You only need to check the pressure dropped for 1 meter. And make sure that this pressure drop in 1 meter is not more than 0.5 kilopascal per meter. And you can use the new inside diameter to calculate the velocity. You've done it before in a class, so revise your class exercises. And check this step 5 as well. If pressure drop is less than 0.5 kilopascal per meter, accept line size. If it's more than that, then consider increasing diameter and recalculate velocity and pressure drop. Now, you want to divide total pressure drop by the length. You may do that, but you need to state your assumption. The assumption will be constant diameter. Secondly, same type of material, for example, commercial steel, carbon steel, copper, bronze, throughout the entire length of the pipe. And also a constant velocity, a constant temperature and pressure. So you have to state all this assumption. Only then you can get a full mark. But I suggest you don't do that because there's a risk. Just take it to be 1 meter. Although you can take total pressure drop and then divide by the total length. For example, total length is 200 meters. You can do that, but you have to state assumption. But don't do that because sometimes marks will be deducted if you forgot to state the assumption. Assumption, constant diameter for the 200 meters. Secondly, the velocity is constant, same temperature and pressure for the fluid and throughout. And thirdly, same material. Same material, if it's a carbon steel, it's carbon steel for 200 meters. This is what happened in the mid-semester test. Some of you were penalized because they did not state the assumption. All right, then we go on. So learning points, this is a summary. You don't have to copy this, you don't have to take picture because this is inside the blackboard. Now we go to a new topic. Now this new topic is on the venturi and the orifice plate. By now you should know what's annular area. Now this one is the float. The annular area is this area here. This is the glass wall. For example, this is a rotometer, this is a glass wall. This is the top view of the float, top surface of the float. So between this and this is circular. So this circular area is the annular area. This is known as annulus. So in a variable area flow meter, the fluid flow area changes with flow rate so that the net force acting on the float is 0. Now this one is the standard orifice plate. This is venturi. Now remember that for venturi, the fluid is coming in from the left side. This is P1. This is P2. This one is known as a pressure tap. This is pressure tap. This is upstream pressure tap. This is downstream pressure tap. Remember your process instrumentation control. You connect a tubing. Now this tubing is a very small diameter pipe, maybe 1/8 of an inch or 1/16 of an inch. You connect the tubing. This tubing is made of metal, carbon steel or stainless steel. So this is high pressure, this is low pressure. High pressure connect to the high pressure side of the pressure cell, differential pressure cell, DP cell. This is low pressure. Low pressure connect to the low side of the differential pressure cell, DP cell. DP cell has got a pressure sensor. The pressure sensor will sense the delta P, P1 minus P2. And this delta P is converted into standard signal, such as the 4 to 20 milliampere. So 4 to 20 milliampere is the output of the DP cell. But the DP cell is not shown in your notes. Now this is a venturi with 3 sections. This is called inlet. This is the throat. This is outlet. You can see that the diameter becomes smaller and smaller, but gradually. We call this a converging cone. The throat, constant diameter. This is outlet cone. We call this a diverging cone. Diverging cone because diameter becomes bigger and bigger, but slowly. Converging cone, throat, diverging cone. There's a pressure drop, but it's not so drastic. Whereas for the orifice, the pressure drop is very drastic. Suddenly, the diameter decreases from the pipe inner diameter to the orifice bore diameter, BORE. BORE refers to this one, the bore. So there's a sudden decrease, and therefore the pressure loss across the orifice plate is higher than the pressure loss across the venturi. Now similarly, you have a pressure tap, is not shown here. There's a before orifice, there's a pressure tab. After orifice, there's another pressure tab. So you have high pressure, you have a low pressure. You don't have to derive the equation, but you need to memorize the equation. This is for Venturi, 0.1, 0.2, P1, P2, V1, V2, Z1, Z2. Z1, Z2, no need to consider because this is horizontal, so there's no change in the height. This D1, the pipe inner diameter D1, pipe inner diameter at the throat D2. This is the diameter ratio D2 over D1. This formula you need to memorize. Q is a meter cube per second. It's not kilogram per second. This is meter cube per second. So I want you to remember this is meter cube per second. It's not kg per second. V2 or V1 meter per second. Beta, diameter over diameter, meter and meter will cancel. Unit will cancel. So this beta is dimensionless. Now this is for the orifice plate. 0.1, 0.2. See that the beta is defined as D2. This is D2. D2. This is D1. So D2 divided by D1. This is called diameter ratio beta. D2, the diameter here, divided by diameter here. That's beta, diameter ratio for Venturi. Now, what's the difference between this formula and the Venturi? Venturi, there's a C0. There's the orifice discharge coefficient. Now, this is to account for the effect of frictional loss on the pressure drop. When there's a frictional loss, the pressure drop will be greater than usual. Now, this case here, you realize that the C0 is not there. C0 is assumed to be 1, but in practice it's not 1, it's close enough, 0.98. Now C0, 0.98 is close enough to 1, so we just ignore the C0. But for orifice, you cannot ignore. The C0 is around 0.6. But to make sure that you get the accurate number, though, because I said 0.6 is an average, it's just an average figure, you have to use this chart here. In the mid-semester test, a lot of people forgot about this. Again, please make sure that you're expert in calculating Reynolds number. Make sure you do that. You make sure you're expert in calculating Reynolds number, because again, I mentioned just now, you got the Reynolds number right, you get 1 mark. Even you don't do anything after this. So this is 10 power 3. This is 1000. This is not 2. This is 2 times 10 power 3. This is 2000. This is 4 times 10 to the power 3. This is 4000, 6000. This is 8000. 10 to the power 4 is 10,000. This is 2 times 10 to the power 4. This is 20,000, 40,000, 60,000, 80,000. 10 to the power 5 after 80,000 is 100,000. So just be careful about this. So this one is okay. This is linear. So the first thing you need to do is just look at the beta, the diameter ratio, D2 over D1, and look for Reynolds number. So let's say Reynolds number is here. This is 10,000. Then you look for this. Okay. So you can see that this is quite close. Then you say, oh, this is about 0.64, 0.65. So if your Reynolds number is very high, 1 million, 1 million is beyond the chart. Take it to be constant. It's beyond the chart here. Say, oh, maybe you can assume 0.62 around here, 0.62. But then you say that it's beyond the chart. It's 500,000 and 1 million. So it's to the extreme right hand side. But you need to calculate this ball Reynolds number. It's based on V2. V2. Remember this. Where's the V2? V2 is here. It's based on this V2 here. This one here. This is based on the D2. All right, so we finished this rotometer, orifice, and the Venturi. Now we go to the pump. Now for pump, most of the time in the chemical industry, we use centrifugal pump. For continuous flow, the toluene is not viscous. Don't need high pressure, so just use centrifugal pump. If you want high pressure, use high pressure. You use a gear or screw. These are rotary pump screw. That means that it's like a screw inside the pipe. So that's rotary, but reciprocating. This is good for very viscous liquid. You can also use a gear or screw or loop for viscous liquid. Now, if you're dealing with a food, you think of a food manufacturing, you don't want contamination, so that the food cannot touch the metallic part of the pump. You want to separate the food from the metal part of the pump. You don't want the metal to go into the food. Then use diaphragm. Because a diaphragm will prevent the food from being contaminated by the metallic part of the pump. You want high pressure, you can use a plunger and a piston. Now this one you have to remember, maximum flow rate. What are things you need to consider when you select a pump? Maximum flow rate, developed head and operating conditions in terms of temperature and pressure. And developed head. Now developed head, in this case here, you just imagine the pump. After the pump, we have a discharge pressure. Before the pump, you have a suction pressure. So the pump discharge pressure minus the pump suction pressure. Discharge minus suction. That is known as developed head. The head that's developed by the pump, the additional pressure created by the pump. Remember, the pump is for liquid, compressor is for gas. Now this is very important. You need to memorize the definition. What is pump head or developed head? This is very important. What's brake power or pump power? Efficiency, this was between 0 and 1. And net positive suction head required, NPSHR. Now, if you look at this one, developed head decreases when flow rate increases. This one makes sense. It's a Venturi principle. Remember the kinetic energy and the flow energy. Kinetic energy is a half V square. The flow energy is the pressure over rho. Rho is the density of the liquid. And you just ignore the potential energy due to gravity. So when flow rate increases, the V square increase, but the pressure will decrease because V square over 2 plus the pressure over the density is a constant. It's a constant drop. So if a V square goes up, to make it constant, the P must go down. V goes up, P must go down. So that when you add up these two numbers, it must be a constant. Therefore, when velocity goes up, the Q goes up, volumetric flow rate goes up, V square over 2 goes up, the pressure goes down. The pressure is for the P over rho. P over rho, that is the flow energy. And vice versa. Efficiency, this is the maximum efficiency, this one here. The brake power is defined here. The mass flow rate times the pump work. WP is a joule per kilogram. Net positive suction head required is this one. Now, if your net positive suction head available, if available is below the curve here, then the gas bubble will form inside the pump. And when the gas bubble bursts, it will create cavitation. Because the gas bubble, when it bursts, it creates a very tiny jet. Now this jet is like a liquid needle. It will damage the internal part of the pump. So make sure that your net positive suction head available, NPSHA, is above this curve. Above this curve, then we are safe. There will be no pump cavitation. It's below this, then we have pump cavitation. Therefore, in the mid-semester test question, it says what's going to happen if your flow rate is very high. If flow rate is very high, this curve will, just imagine this curve, will just go up this way. When go up this way, then there's a chance for NPSHA. The NPSH available lies below this black curve, there's a greater chance, there's a more risk that NPSHA lies below this, and therefore there's a higher risk of cavitation for high flow rate. Now this one is very important. Best efficiency points here. Just you don't have to memorize all the numbers here, but the pattern you need to memorize. Say, oh, this is x-axis is the meter cube power, so this is down. Efficiency is here. You can see brake power is going up. NPSHR for higher flow rate, this will go up very drastically. Just extrapolate this, it will go up very drastically. And there's a higher risk of cavitation over here because there's a greater chance that NPSHA is below this black curve here at very high flow rate, and that results in a cavitation. What is HP? HP horsepower, yeah. HP, you see a unit HP horsepower. If you see the other topic, gas liquid separator, the HP separator is a high pressure separator. Now we finished the pump, so we have to move more quickly. Compressor. All right, I don't want to repeat this. You can find this in your notes. Don't memorize this one. Don't try to memorize the figure. You can see the range for inlet capacity. If you want to have very high flow rate, just remember, use centrifugal compressor. Remember, compressor is for gas. Huh? You cannot have a liquid inside the going into the compressor, because the liquid, when it enters the compressor, is like flying bullet. It's a liquid bullet. It will damage the internal parts of the compressor. In terms of maintenance, centrifugal compressor, low maintenance, reciprocating type, high maintenance. Because this one involves moving parts, a lot of moving parts. Now the one that's okay, this one you know, the COWS table, COWS table. Go back to your materials for design, MFD. You can use a COWS table to decide whether to use centrifugal or reciprocating compressor. Now this one I already explained, so I'm not going to repeat this. Isothermal, all the curve that, all the points that lies on the curve has the same temperature, so it's isothermal. Isothermal, constant temperature T1, T2, T3. All the points that lies on the rate curve will have the same temperature T3. This is pressure, this is volume, ideal gas equation of state. Now this is isothermal compression. From this point to this point, higher volume, lower pressure, constant temperature compression, is smaller volume, higher pressure. This is isentropic compression, adiabatic. Adiabatic means that Q in equal to 0, Q out to 0. There's no heat transfer, no heat going into the compressor, no heat getting out of the compressor. So that is isentropic, constant entropy, or adiabatic. It's from here to here. And there will be a rise in it. It will give rise to an increase in temperature. Now this is polytropic, and the compressor is most likely to be polytropic type, this one here. But you have the index, compression index, N. It's between 1 and gamma. Gamma is a CPOCB. This definition here, CPOCB. Now this number will be given, this gamma here. Don't memorize this. No derivation. There's no derivation on this. Don't try and memorize this formula. You just need to revise the exercises, the tutorial. This one I already explained in the class. It has been uploaded last night. You can see the answers for the exercises. Don't mix up compression ratio with compression index. Ratio is a final pressure divided by initial pressure. We call this ratio. Index means this one. And N is the index, compression index. When you see the word ratio is a P2 or P1. The final pressure divided by the initial pressure. So you call this compression ratio or pressure ratio. Right, I've shown the derivation in the class, so I'm not going to repeat this. Okay, this one you've seen it in the class. Now this one is a reciprocating compressor. Realize that there's a crankshaft. There's a driver here, this connecting rod. This is called the piston. This whole thing, the box here is a cylinder. Suction is for in, discharge for out, in and then out. Suction valve, inlet valve, discharge valve, outlet valve. Of course, the crankshaft is connected to a driver. So this driver could be electric motor. It just is not shown here. This one I already explained in the class. What is V1, what is VS, VC, and the VF? You just have to read out on your own. Inlet valve and exit valve. Okay, this I already explained in the class. I'm not going to repeat. Revise the exercises for this, how the calculation is being done. I did mention there's a difference between PV equal to nRT and PV equal to mRT. M is a kilogram. This is a kilogram. This R over molecular weight, relative molecular mass, MR. R over MR. So unit here. All right. This is in terms of kg, kilogram. Right. Remember this. The kilogram. This is the relative molecular mass or molecular weight of the gas. R is 8.314. T is Kelvin. P2 is the absolute pressure. Let's say bar absolute or Pascal absolute. P1 is also absolute pressure. The work you can easily calculate. Remember, this one is for the reciprocating compressor. This one here is for this type of compressor. Now this is there's a workout example over here. All right, you can check the numbers over here. There's a work input per unit mass, so many kilojoule per kilogram. Again, the formula will be given. Don't try to memorize this formula. Centrifugal compressors are commonly used. If you want high pressure, use the reciprocating compressor, also known as the piston type. There are three conditions: isothermal, isentropic, polytropic. This one, work input per unit mass. This is for centrifugal. Work done per cycle. This is for the reciprocating compressor. So that's why you have two sets of formula. Now this one is for the reciprocating compressor. This is the piston type. This is centrifugal compressor. This is the take note. All right, this is centrifugal. So this is centrifugal. These set of formulas for centrifugal compressor. Centrifugal. Reciprocating compressor is another set of formula. This is reciprocating compressor. And that's why you have two sets of equations. All right, so this one you need to memorize all the definition. I've shown the working in the class. The important part is this. You need to mentally, you have to mentally visualize. Mentally visualize this. Polytropic head, surge point, choke point, shaft power, and the efficiency. This one is the important part. You cannot have, this is for centrifugal compressor. Right, surge point, choke point is for centrifugal compressor. This is not for the reciprocating compressor with the piston, not for that type. This is for the centrifugal compressor. The surge point, choke point. When gas flow drops below surge point, discharge pressure will drop, resulting in flow reversal. So if your flow rate cannot be too low, otherwise the molecules will go backward inside the centrifugal compressor. So the molecules will be oscillating. It will go backward and then forward, and then repeat backward and then forward. Now this molecule oscillation will make the system unstable. It's like oscillating flow, and you cannot control this oscillating flow. And this oscillating flow will damage the internal part of the reciprocating compressor. The other one is called choke point or stone wall. When the gas flow reaches choke point, the flow rate cannot be increased any further. That's the limit of the flow rate. So you need to operate between surge point and choke point. Usually you don't operate very near to the surge point. You don't operate very near to choke point. You like to operate somewhere in between. You need to give some margin for here, some margin for here, somewhere in between. That would be very good operating range for the centrifugal compressor. And over here, why we need to use suction drum, why you need to use a cooler. You can have this kind of question, why you need cooler? Why you need cooler? You need cooler because compression means reducing volume. If you reduce the volume, pressure increase, temperature increase. Unless it's isothermal, but very unlikely it's isothermal. More likely to be polytropic. Volume decrease, pressure increase, temperature increase. Therefore, you need to cool down the gas. Because if you allow the high temperature gas to pass through the pipe, through the equipment and so on, it will weaken the material. The strength of the material will become weaker. High temperature will weaken the material. It will affect your U point, decrease your U point. It will decrease your ultimate tensile strength. All this you must remember. High temperature is no good for U point, no good for ultimate tensile strength. As you have seen that in your MFD first year. Then the suction drum is to knock out any liquid from incoming gas. Why? This one I mentioned many times. Why is it better to have two compressors instead of buying one big compressor? If I buy one big compressor, very expensive, big compressor use a lot of energy, so it's no good. Big compressor use a lot of energy, is no good. very expensive. And furthermore, if I just use one very big compressor, the temperature will go up very drastically. And then how do I cope with very high temperature? I need to have very expensive material, special alloy, to cope with high temperature. So instead of doing that, instead of buying one very big compressor, I use two smaller compressors. So this smaller compressor I call it stage 1 compressor. There's an intercooler, then followed by the stage 2 compressor. Now this one is a typo error. This is after cooler, AFTER, after cooler. This is correct. This is intercooler. So I do a intercooling, reduce the temperature first, then send it to the second compressor. After that, I do the after cooling. So I don't need to have very expensive special alloy for this pipe here. Now that will be needed if I use one single big compressor. Expensive and also consume a lot of electricity. Because the compressor is, in this case here, I just take it to be driven by electric motor. Please study this one. This is very important. Study search point, choke point is very important. All right, so I finished this slide here. Then we go on to next one. So any questions so far? Heat exchanger. Now, heat exchanger, there's one long question. The 20 marks question is a heat exchanger. Don't throw away your answers for the CA, part 2. You need that, you need to study that. For heat exchanger, this one you have seen it before. What is the shell? What's the tube? So no need to repeat. Now this one, you can see shell and tube exchanger. Now this is the shell fluid. Right, it's a shell fluid. And this blue one is a tube fluid. You see the several tubes or many tubes. They make a U-turn. Therefore, we call this the tube bundle. The shell fluid is outside of the tube. The tube fluid is inside the tube. So the fluid inside the tube cannot touch. There's no way the fluid inside the tube can touch the fluid outside the tube unless there's a leakage. In this case, there's no leakage. Therefore, the fluid will stay inside the tube. It cannot touch the shell fluid. Baffle. Revise this part. Can your baffles be too near to each other? Answer is no. Why cannot be too near? Do you like your baffles to be very far away from one another? It's also not desirable. Why cannot be very far away from one another? Why it's also no good to be too near to each other? Basically, it's to encourage mixing. The baffle is to encourage this mixing here. And also this baffle length, it cannot be too long. It can too long, not enough room for a fluid to change the direction. This one everybody knows. This is a fundamental relationship. I suggest that when you do a calculation, forget about the negative sign. The negative sign is the one that's confusing. Just pretend negative sign is not there. Just do your normal calculation. Delta T, take the high temperature minus lower temperature. Forget about negative sign. Same also. Forget about your negative sign. Delta T is higher temperature minus lower temperature. Delta X is a thickness, wall thickness. The K is a thermal conductivity. Unit is watt per meter per Kelvin. W over M dot K. This is the Fourier's law of heat conduction. Now this is the A bar. See, there's a bar on top. This is the log mean area. This one you need to memorize. This is the Newton's law of convection. There's a H. Again, forget about negative. Now this is the convective thermal resistance. You need to memorize this. The H, O, H, I. Now this U, O. Now this is the overall heat transfer coefficient. It's based on the outer surface area. This is the inner. This is the inner temperature T1. This is the outer temperature T2. Inner radius Ri, outer radius Ro, length. You need to memorize this formula. This one, the Hi is for the inner wall surface. It's a heat transfer by convection. Heat transfer by convection from the bulk of the liquid or bulk of the steam to the inner wall surface. That's a Hi. Ai is based on Ri. The second term, delta R is a wall thickness. Delta R is R0 minus Ri. R0 minus Ri is delta R. K is the thermal conductivity. The A bar is defined over here. But later you see that. That's a definition for A bar. You can find that in your notes. And the HO is for the outer surface. So the UO is the overall heat transfer coefficient. So this second term is for conduction through the pipe wall. The third term is from the outer surface to the environment or to the surrounding. That's the third term. This one you must memorize. Must memorize Nusselt number, Reynolds number, and Prandtl number. Now remember this. The K here, the K is a thermal conductivity of the steam, thermal conductivity of the water, thermal conductivity of a liquid. The K is not the thermal conductivity of the stainless steel. That is not what it means. The K here, the K is the thermal conductivity of the fluid, not the materials of construction, not the stainless steel, not the bronze and so on. That's for the fluid. Same for viscosity and the specific heat capacity. All these are for the fluid. Whereas this K here is the thermal conductivity of the carbon steel. This K here. This K here is the thermal conductivity of the steam, of the water and so on. No, there's no need to add in the negative sign. Just because negative sign is a confusing part. Don't forget about the negative sign. Just do your normal calculation. No need to memorize. No need to memorize this. This is laminar flow, no phase change. No phase change means if let's say this is a gas, it remains as a gas. If this is a liquid, it's always liquid. If this is steam, it's always steam. The steam doesn't condense. So that's meaning of no phase change. Steam cannot condense. Or there's no condensation of the vapor. No phase change. Vapor is vapor, remain as vapor. Liquid doesn't evaporate. Liquid stays as liquid, no evaporation. So that is no phase change. No condensation, no evaporation. Again, please remember this K is for the fluid. The mu here is the viscosity. This is a absolute viscosity. If it's a CP, centipause, Centipause, you must change to Pascal second. To change Cp to Pascal second, just times 10 power minus 3. Now don't forget this, you can lose mark because you forgot to change Cp into Pascal second. And the Cp here is the specific heat capacity. All right, joule per kilogram per Kelvin. That's a Cp. This is for turbulent flow. Again, don't memorize this. This is based on Cedar and Tate. This one must memorize. I repeat, this one you must memorize. The equivalent diameter or hydraulic diameter. This is very important. And study this one. You will see the capital D and a small d. The capital D is for big pipe. I just call this big pipe. This is a small pipe. Small d means DO, outer diameter of small pipe. DI, inner diameter of big pipe. Capital D, big pipe. I is inner diameter. Small d, small pipe. O, outer diameter. This is a small d, DO, outer diameter of small pipe. Now for flow outside the tube laminar, no phase change. This is for the heat exchanger. They use the equivalent diameter, DE. And therefore, I mentioned this is very important. You must know how to calculate this DE. For flow outside the tube, now this is turbulent flow. This is laminar flow. No evaporation, no condensation. No evaporation, no condensation means no phase change. No phase change, no evaporation, no condensation. This is outside tube means shell. This is shell side. Outside tube is shell side. This is another correlation. Don't memorize this one. This is triangular tube arrangement. Now, what's the difference between rating and sizing? I mentioned it many times in the class. Rating means you already got heat exchanger, but you suspect that the heat exchanger got fouling. So you want to check, is it true? The heat exchanger got fouling. Therefore, the Q is smaller than what we think. You want to figure out. This is called rating. Sizing is different. Sizing means I'm thinking of buying a new heat exchanger. I want to find what is the total surface area required. I want to calculate the area. I don't have a heat exchanger now. I'm thinking of buying one. So I need to calculate the area. That's called sizing. Remember this formula? This one must memorize. Must use LMTD. Then you're wondering, how come there's no correction factor? How come there's no FT? There's no FT because this is one shell pass and one tube pass. 1-1. This is 1-1. Exchanger, no need FT. FT equal to 1. It's always 1. It's only when you have a 2 shell pass or you have a 2 tube pass or 4 tube pass, you have a 4 shell pass, this one. Only then you have to look at the chart and find the FT. If it's 1 shell pass and 1 tube pass, FT is always 1. Right, so there's a correction factor, FT, over here. So in our case, if it's 1 shell pass, 1 tube pass. Also remember, read the exam question carefully. If it's 1 shell pass, 1 tube pass, don't waste your time and look for FT. FT is always 1. No need to use the chart here. So it's very important, read the question very carefully. Again, don't memorize this formula. This is for the inner convective heat transfer coefficient. No evaporation, no condensation. There's no phase change. This is flow through a shell, triangular tube. and it's a square tube. So you could be asked, when do you use triangular tube arrangement and when do you use square tube arrangement? So think in terms of pressure loss. Which one got more pressure loss at the shell side? Triangular or square? Now, which one is easier to clean? Just outer surface, which is easier to clean? Triangular, easier to clean, or square, easier to clean? And so on. So think in this way. Now, this is for dirty overall heat transfer coefficient. You consider the fouling coefficient, FIFO. This one you've gone through. Please revise your CA. I hope you have not thrown away your answer for CA. This is a TEMA standard. Just be aware there's such thing called Tubular Heat Exchanger Manufacturers Association. Length of the tube over the shell diameter. Remember, it must be between 5 and 10. So if you see the question like this, please check L over D, length of the tube divided by the shell diameter. It must be between 5 and 10. Cannot be less than 5, cannot be more than 10. The reason is that your heat exchanger, there's a layout, all right? So you need to make sure that layout is not awkward. And you think of people who are trying to install the heat exchanger at the plant site. So we should at least not make the layout awkward. When layout is awkward, then how about the piping? The piping must go around the heat exchanger in a very awkward fashion. All right, so this one reflect on this, very important. What are some considerations when deciding on the types of shell and tube exchanger to use? Is it a fixed tube, sheet design, floating head, U-tube? This one is very important. This one also, study this one. And the tubes, what are the factors? Tube design, tube arrangement, tube pattern or tube arrangement, triangular, square, rotated square. Think in terms of fouling, pressure drop, ease of cleaning. You could be asked this kind of question. And wall thickness also. These long questions, more theory, not much calculation. There'll be calculation, but not much. Right, any questions so far? Now shell, now let's look at shell side. This one, you have to know what's a baffle cut, etc. This one you can find in your notes. Spacing, yes, spacing. Can your baffle spacing be very narrow? Can it be 0.1 meter or 0.1 times the shell diameter? What happens if your baffle spacing is very narrow? What happens if your baffle spacing is very wide? 2 times the shell diameter. You think of the flow pattern. Is there any effect on the flow? If it's very wide, you think that all the tubes will have a chance to come to contact with the shell fluid? It's very wide, yeah? Very wide, very wide. You think all the tube surfaces will have good contact with the shell fluid? It's very narrow. What's going to happen? Very narrow, pressure drop. Think of pressure drop, very narrow. The baffle very near to each other. Will there be effect on pressure drop? This is also very important. All right, you just have to memorize this one. When you answer this kind of questions, don't just say tube site. Don't just say shell site. Please give a clear explanation. We don't like high velocity. We know that now that depends. High velocity gives rise to high heat transfer coefficient and reduce fouling, but high velocity also results in high pressure drop. So there's a trade-off over here. So don't want velocity that's too high. Yes, it's good for heat transfer coefficient, also can reduce fouling, but it can also result in high pressure drop. All right. You read the questions. Sometimes it's stated as a shell fluid, as they say A or B, and it will be stated fluid A is corrosive or non-corrosive, high pressure, and so on. It will be stated in the questions. This is one way the questions can appear. Another way the question can appear is that the name of the chemical is stated. Therefore, by looking at the name of the chemical, and based on your general knowledge of the properties of the chemicals, you will know which is corrosive and which is not likely to be corrosive. So the two ways that information can be presented. All right, again, need to memorize this recommendation: tube site, shell site. Not so much of vapor. Focus more on the liquid, tube site and shell site. Look at the range here. For liquid, all right, viscosity should be less than 1 cp. Maximum allowable pressure. This is for the entire. This is right. This for the entire heat exchanger. For the liquid, entire heat exchanger. It's not per meter. It's for the whole heat exchanger. Should be less than 35 kPa. That's for liquid. If your viscosity is less than 1 cp, if your viscosity is from 1 to 10 cp, the maximum allowable pressure. Sorry, this is the pressure. Maximum allowable pressure, 35 kilopascal. If your liquid viscosity is 1 to 10 cp, the maximum allowable pressure will be 50 to 70 kPa. This is for the whole heat exchanger. That is pressure. This is velocity. All right, so your CA, you use the Kern's method. At the end, you need to calculate the percentage difference in the U. So revise that portion. Again, I want you to think about it. What's the effect of baffle spacing? If let's say the baffle spacing is too narrow, 0.1 times the shell diameter, what's the effect? In terms of pressure drop and overall heat transfer coefficient, if your baffles are spaced far apart, 2 times shell diameter, what's the effect on pressure drop and overall heat transfer coefficient? What's the effect of baffle cut on this, wall thickness on this, and the diameter on this? That's how you should revise for this module. Look at this factor and then reflect on it. Same for this one. That's how you should revise based on this. Look at this and then think about it. Look at this and think about it. Okay, we go to the last portion. You're very quiet. Do you have any questions? The last part is on mass transfer equipment. All right. Okay. What type your question? Okay. Do we need to do a second round of calculation if velocity and pressure drop not in the range? The answer is no. All right. Any more questions? Okay, this is mass transfer equipment. I have explained the theory behind this. So my purpose is not to repeat the theory, but the idea is that the separation principle is the difference in volatility. That's separation process. Now always remember any substance with lower boiling point is more volatile. Any substance with higher boiling point is less volatile. More volatile, like those substances that's more volatile tend to be enriched. They tend to be enriched in a vapor. The less volatile substance tend to be enriched in a liquid. And you just have to visualize this picture here for the vapor liquid separator. What is the purpose of inlet diverter? I already explained the purpose here. You can find explanation in your notes. What is the use of the gravity settling section? What's the use of the liquid collection section? And when you use vertical and horizontal separator? All right, so this is a comparison. Basically, it's based on geometry. Study this one, vertical and horizontal, study this. Could be asked questions related to the comparison between vertical and horizontal separator. This is a typo error. This gravity settling section. So you need to be aware of the purpose of each one of these. And this one is separation, all right, into vapor and the liquid. We've done the exercise in the class, Dalton's law, Raoult's law. Just revise this part here. Phase equilibrium constant K. You just need to revise this. We're not using the Priester chart in the exam. There will be no the Priester chart. This one you must remember the definition of relative volatility, Ka over Kb. How to get the, this is a typo error, this is Kb, this is Ka, okay, this is Kb, which I mentioned in the class. How do you obtain the K value? There's an exercise, you have to use the Antoine equation. This one you just need to memorize. This in terms of mole fraction. X for liquid, Y is for the vapor. A is for component A. We're using binary system, so the two components A and B. Okay, it's a definition of the relative volatility in terms of the vapor pressure of pure substance. This is the saturated vapor pressure. This is the Antoine equation dimension. Be careful of the units. mm mercury, Kelvin. Okay, study this one on your own. This one you can study on your own. And this one I mentioned in the class. I'm not repeating this portion here. The other thing is that in the exam, the time is the premium. Don't plot the graph. Don't waste your time to plot the graph. You plot the graph, you're wasting your time. I suggest that you want to get the point of intersection, solve the equation simultaneously. How do you get the point intersection in your secondary school? You solve two equations simultaneously. You get a coordinate xy. That is at the point of intersection. Try to avoid the graph as far as possible. Okay, this is the theory, the design, which I already explained in the class. It's based on the terminal velocity, and there's a constant K. This is the flash drum constant. Rho L, this is the liquid density, this is a vapor density. Remember, you want vapor to go up. You want liquid to fall down by gravity, due to gravity. Vapor goes up, liquid comes down due to gravity. That's why you call this gravity settling section. Mist extractor is to trap any of the tiny liquid drops that may escape through the vapor outlet, but we don't want it to escape. Therefore, you put a mist extractor. The mist extractor is like a wire mesh. It's a physical barrier to trap the tiny liquid droplets. Now, VV max, this is the principle behind the calculation of the minimum diameter of the drum. I already explained in the class. K drum, you can see the range 0.03 to 0.11 meter per second. The height here, you can see the three section, HV, HF, HL. When you put your answer, just use the minimum 48 inch, use the 18 inch. No need to calculate, just memorize the number. The one that you need to calculate is this one, the liquid hold up time. It should be stated in the question. If it's not stated in the question, then you have to assume what's the liquid hold up time. And make sure that the height of the drum divided by drum diameter is between 3 and 5. Okay, there's an exercise here. You can refer to your notes. How do you do all this calculation? Okay, you can refer to your notes, and the answers also posted in the blackboard. Now this one, this is very important. So for long questions, please concentrate on this. I already mentioned if what's going to happen if I increase column pressure. Higher column pressure, higher dew point. Higher dew point means easier to condense. Easier to condense means my condenser uses a coolant. I can afford a coolant that's warmer. So usually I use 2 degrees Celsius, 2 degrees Celsius cooling water or 2 degrees Celsius chilled water. Now I increase the vapor pressure. Column pressure means the vapor pressure. I can afford to use 10 degrees Celsius chilled water. That is good for me because it will reduce my operating cost. Because to produce a chilled water is not free. There's operating cost involved in chilling the water. Effect of reflux ratio. Reflux ratios, this is called external reflux. Internal reflux means the liquid flowing from one tray to the next tray. We call this internal reflux. This is a feed point. This is number 7, number 8. Your feed location is number 8, not number 7. Remember, number 8. In your Aspen HYSYS, this is 0. This is 1, 2, 3, and so on. And this is 14. Sorry, yeah, this is 14. And this is 15. 0, 1, 7, 8. 8 is the feed location. 14. And then Aspen, take this as number 15. Reboiler is 15. Okay, so study this whole thing. Don't just memorize, you must understand the meaning of this. What is a rectifying section? What's a stripping section? This one I already explained in the class. Definition, L over D. There's a reflux ratio. Optimum reflux ratio is 1.2 to 1.5 times of minimum reflux ratio. The minimum reflux ratio is a ratio at which separation is achieved with infinite number of stages. If D equal to 0, it means that everything becomes reflux. If everything becomes reflux, we call this total reflux. Total reflux is the opposite of minimum reflux ratio. So when you have a total reflux, your L over D, D is 0, L is a positive number, L divided by 0, the answer is infinity. It means that your external reflux ratio is infinity. And you have minimum number of tray. That is for infinite L over D, minimum number of tray, because D is 0, L is positive. Whereas this one talks about minimum reflux ratio. L over D is a minimum, maybe 0.83. There's a minimum reflux ratio, 0.83. Then the number of stages is infinite. Whereas for total reflux, D is 0, L over D is infinity. The number of trays is minimum. Okay, remember this. I mentioned many times in the class, if I tell you the spacing between one tray and next tray, and tell you the number of tray, you should be able to estimate the height of the column. Spacing between one plate and the next plate. 0.15 to 1 meter. 0.6 meters is most commonly used. The spacing. It's a plate spacing. This formula is very important. The K is a function of plate spacing, VV max. Very similar to the flash drum. The concept is taken from the flash drum. All right, the extra space, this is a very important question. Extra space, you should consider what's the liquid hold up. At the bottom of the distillation column, there's liquid, meaning below the below the last tray, the last plate, you have a room to hold the liquid. So you have to assume what is the liquid hold up time. Let's say 5 minutes. From there, using the same method as the one you have seen for flash drum, you can estimate the height of the column below the last plate. So for this one, you got to revise the exercise on the flash drum. How to calculate the liquid hold up height. You refer to the flash drum, the calculation is the same for distillation column. It's basically based on time. How long do you want to hold the liquid? 5 minutes or 3.5 minutes and so on. Now this one is the same as the one for flash drum. You've done it before in the class. This is a cross flow plate. You can see here. This one. Cross flow because vapor is going up. Liquid is here, right angle. The three kinds of plates: sieve, bubble cap, and valve. I asked you to study this one, the aspect and the three types of plate. Lowest cost is sieve. Most expensive is the bubble cap. You can see here. Downcomer. This the downcomer is a drain pipe. Downcomer. You can see here. And this is the downcomer top width. What's the weir? Weir is this one. Weir height. So your aspen, you see this tray diameter. What is the flow path length is defined here. What is downcomer top area? What is downcomer bottom area? What is bottom weir length? What is the top weir length? All this you have to go through it one by one on your own. What is flooding? Flooding is when the liquid keep on rising. You think of a river. If the water inside the river keep on rising, it will overflow. It will overflow to the road. It will overflow to our garden. It will overflow to the house and so on. So that's the meaning of flooding. Flooding means the liquid level keep on rising until the liquid touches the tray above. When liquid touches the tray above, this entire tray section is flooded. That is liquid flooding. How can you have liquid flooding? You have liquid flooding when velocity is very high. Vapor velocity is very high. So a lot of vapor rushing in, push the liquid level up. A lot of bubbles, a lot of vapor, a lot of gas bubbles inside, push up the liquid level until the liquid touches this tray. That is called flooding. Now downcomer backup means this somehow it got choked. There's some kind of debris obstructing it. Maybe there could be impurities or debris or whatever. Therefore, the liquid cannot flow smoothly. If the liquid cannot flow smoothly, the liquid level will rise. It keep on rising here. This is downcomer, it's like drain pipe, keep on rising. And then it will overflow. Just a kitchen sink. What happens if a drain pipe is choked? Then the water cannot pass through the drain pipe, and then the water will overflow and go to the kitchen floor. It's the same idea. This is called downcomer backup. This is very important. The 3 points here. Plate should be sized to give optimal vapor velocity. How do you calculate the flooding condition? What is the vapor velocity of flooding condition? We call this upper limit. What is the vapor velocity of vipping condition? We call this lower limit. Okay, rating. I think you missed this part. I did mention just now. Rating means that you already got a distillation column. Your distillation column is already working. It's working, but you just want to find out is a number of tray still appropriate? Let's say now you got 23. Should I stick with 23 and still achieve a purity of 96% benzene for the distillate? So that's a example of rating. Do I stick to the same number of plates, or do I stick to the same LOD, reflux ratio, and still achieve the 96% benzene purity for the distillate? Distillate is a top product, so we always refer to the 96% benzene. All right, when you talk about rating, but that is for your existing distillation column. When you don't have any distillation column and you're thinking of buying new one, that's called sizing. Yes, indeed. The reasons are similar. All right, so this one is the okay, flooding velocity. But now the K is dependent on plate spacing, streams flow rate, liquid flow rate, vapor flow rate, and the liquid and vapor density. And velocity is set at 70% to 90% of the VF. Remember this. Now this one, listen very carefully. This is the liquid vapor correction factor or factor. This is the mass flow rate. W is a weight, W-E-I-G-H-T. This is a mass flow rate. Mass flow rate means a kilogram per hour, kilogram per second. It doesn't matter. As long as kg per something. Kilogram per hour or kilogram per second. For liquid, V is for vapor. W is weight, W-E-I-G-H-T. So that is the mass flow rate. This is density of vapor, kg per meter cube. Density of liquid, kg per meter cube. Now this is a factor. K is the diameter of the plate. So diameter of the plate, you can see here. All right. Now how do you get the diameter of the plate? It's from here. First, you need to calculate FLV. Let's say whatever FLV. And you must be given information about plate spacing. Let's say it's here, it's plate spacing. And then you read here. You go here. Then you read this number. This is K. This is the K over here. Be careful. 10 to the power minus 2. This is 0.01. All right, 10 to the power minus 2. 0.01. This is 2 times 10 to the power minus 2. 0.02. 3 times 10 to the power minus 2. 0.03. 0.09. 0.09. 0.1. 2 times 10 to the power minus 1. 2 times 10 to the power minus 1. 0.2. 0.3 and so on. Okay, remember this, huh? Same also. 0.1, 0.2, 0.3. Now come back to here. So let's say you have this. So you have this K factor. So let's say I increase the plate spacing. I increased from 0.3 plate spacing. So I want the plate to be further apart. 0.3 increase to 0.6. 0.6, that's it. Oh, bigger K. And it makes sense because bigger K means VF is bigger. VF is bigger means, if you look at this, now I just imagine I want bigger spacing. So the tray, I mentally move up the tray. I move up the tray, it means that now more room for liquid to hold the liquid. And therefore I can afford to have higher VF. That means I can afford to have higher vapor velocity because now I've got more room. Right? Spacing is bigger. K is bigger. K is bigger, VF is bigger, right? So it means that more room can tolerate flooding better. All right, so this, remember the factor. There's this for F is flooding, 0.85. Okay, study this one. What is the opposite of flooding? Vipping. Vipping is too little liquid. Too little, or rather, you have normal liquid, but your vapor velocity is too low. Vapor velocity is too low. What happened to the liquid? Liquid look for opportunity to go through the hole. So drop by drop. This is called vipping, because vapor velocity is too low. So liquid look for opportunity to pass through the hole. Pass through a hole. This is called vipping. Flooding is no good. Vipping also no good. Flooding can cause the tray to collapse. You think of this hydraulics. The hydrostatic pressure is too high. If it's very high, the tray, some of the tray will be weakened after operating the column for a number of years. It can collapse, and it indeed happen. Tray can collapse. This is very important. You see this in the exam question. Maximum entrainment means this is the vapor mass velocity, y-axis. X-axis is the liquid mass flow rate. If it's between the purple and the dotted line here, it means good. You're between the maximum entrainment and the 0% VIP. Anything above means flooding. It means the liquid touches the tray above, it's flooding. Anything below means liquid starts to pass through the holes and go to the tray below. This is called vipping. This is the minimum wear load. All right, that's for low liquid flow rate. Minimum wear load. This one, maximum wear load. Beyond that, downcomer backup is like drain pipe choke. Drain pipe choke means that this liquid keep on rising, level keep on rising, and then liquid keep on rising because there's some kind of obstruction blockage here, keep on rising, they overflow to here. All right, it's overflow to here. So that is downcomer backup. So downcomer backup is also bad. You can see here, this one. All right, so this is very good. So the operating point is here. So you need to look at it more carefully, because you see this in your exam questions. But you're not. But you need to figure out the operating point should lie within the envelope with the entrainment setting the upper limit, which is flooding, and the vipping setting the lower limit over here. And don't forget there's a backup here. Downcomer backup is also bad because downcomer is choked. And if vipping is very serious, you call this dumping. 100% vip is called dumping. It means the liquid basically just pass through the hole easily. It's called dumping. But before that, when it starts to vip, the liquid will just flow drop by drop. But after that, the liquid flow continuously. And after that, the liquid will flow continuously at high speed. That is called dumping. All right. So that's all. I'll end my session. The next session, I'll send the invite around 1:45 this afternoon.